All right, if you understand the basics of the different types of radioactive decay, let's talk a little bit about the rate at which radioactive decay takes place. So I like this meme because it's pretty much true to what happens here. We can't predict the behavior of a single atom, but we can certainly look at the probability of millions of atoms, and that all centers around the idea of half-life. So it turns out that when a material undergoes radioactive decay, it really decays according to certain probabilities. And because of that, we cannot necessarily predict how long a certain atom will last before it radioactively decays. But by looking at large samples, we can start to make some safe assumptions about how long it takes for half the material to decay, also known as the half-life. So the half-life is the time it takes for half of the nuclei of a radioactive material to decay into a daughter nuclei. To give you kind of an understanding of half-life and how the probability kind of plays out and how this meme makes sense, consider if we did an experiment in which we took 10 million people, each with a coin, and we asked them to all flip their coin. And we said, make a prediction about how many of the coins will be heads and how many will be tails. Most people, for good reason, would predict 5,000 heads and 5,000 tails. And you would be very close because with that large sample and the probability of flipping a head or a tail being 50-50, you could anticipate that about 5,000 would be heads and 5,000 would be tails. On the other hand, if we took 10 people and said, predict how many heads and tails you'll get when you flip the coin, you might say 5 heads, 5 tails, but you would probably find that you do this a series of times. Sometimes you're close, sometimes you're quite a bit off. And so this is the thing with probabilities. The larger the sample, the more accurate or more close the prediction theory is to the reality. If we were to take one coin and flip it and ask you what's the probability or how many of the coins will be heads and how many will be tails, now you are kind of guessing. You could say one head, no tails, or vice versa. And so, yeah, we can predict quantum behavior for millions of atoms, but not for a single atom. Now, half-life then in our analogy, if we ask 10,000 people to flip a coin, at that point, we've gone through one half-life. So we still have all our 10,000 coins, but half are heads and half are tails. That means half are radioactive. It's called the heads radioactive. Half of the other ones, or the other half, are the daughter nuclei. So if we started with, we should say maybe not even radioactive, we should say half of them remain the parent and half of them are now the daughter nuclei. And then if we said, okay, everybody flip your coins again, except the daughter nuclei are down already in a lower energy state, so they're going to stay there. The remaining 5,000 people flip their coins, and now we would expect about 2,500 to be parent nuclei, about 2,500 to be daughter nuclei, or 2,500 still the original radioactive isotope, and the rest have decayed. Then I might ask you, how long do we have to go through this process until everyone has flipped a tail and has radioactively decayed? And the answer to that is hard to predict because in theory, there could be some person who's just extremely lucky, skilled, or whatever, and continually flips heads all the time. And so they go through a half-life and another half-life. And again, this is the strangeness of trying to make quantum predictions for a single atom where it works for millions of atoms. Great. For a single atom, it's a little more questionable. All right, so as we move forward with half-life calculations, if that concept somewhat makes sense, then let's just consider when we talk about half of the nuclei to decay, keep in mind that we can measure or we can get a sense of this in a number of different ways. So the units that we talk about, there's a lot of things that end up being halved. For example, It might be the number of atoms. So we start with 10 million radioactive isotopes. After one half-life, we get 5 million still radioactive. So we could talk in terms of the number of atoms. We could talk about the radioactivity, maybe measured on a Geiger counter. So for example, a Geiger counter might give us 50 clicks on our Geiger counter every minute. So we wait for a half-life, we would then expect half the number of clicks per minute. Radioactivity can also be measured in things called sometimes becquerels, BQ. What's another one? Like I think um, rads or something like that. There's a few different units that people use. In the end, they all are measurements of the number of atoms that are radioactive, and therefore, after you go through a half-life, all these things get halved. You could work in percentage if you really wanted to. The mass will also decay to the daughter. So if we start with 1 kilogram of a radioactive isotope and wait for a half-life, we would expect to see 0.5 kilograms still being radioactive. But that's not the end of the story. Half of that material is still there as the daughter nuclei. So we still have a whole kilogram. So a total of 1 kilogram here, total of 1 kilogram at the end. And so we still have this 1 kilogram amount, or essentially 1 kilogram. Clearly, there's going to be some slight change in mass to create energy. But if you have a scale and it reads 1 kilogram at the beginning, it's essentially going to read 1 kilogram at the end. Point is, half the material has decayed, but the other half is still the existing parent nuclei. So anyway, long story short, half-life, there is no standard unit to measure the amount of radioactive material. There's a number of different ways that it can be done. So we're just going to get used to understand. If you understand the concept of what is being halved, then the different units you can roll with. Before we do any questions, let's acknowledge that the decay or half-lives really depends on the stability of their radioactive nuclei. And we've talked about the different degrees of stability. So if you look at something like lithium-8 on this chart here with its 0.838 second half-life, clearly not a very stable isotope of lithium. If you waited even just 2 or 3 seconds, you would expect most of that material to radioactively decay. Even if you started with, millions of atoms, they would radioactively decay according to a 0.838 second half-life. So after a few seconds, you've gone through already, 3 or 4 or 5 half-lives. So you're down to a very small percentage remaining. Compare that to, say, uranium-235 with its 703 million year half-life. You have to wait 703 million years to take an original sample of uranium-235. And before that radioactively decays and goes through a half-life, you got to 703 million years. And only then are you down to like a 50-50 blend, 50% uranium that you started with, the uranium-235, and then the rest of this material will be, it'll be the daughter nuclei or the daughter of the daughter nuclei. We'll talk about decay chains at some point when it's necessary. But point of this is we have a range of stability. We have a range of half-life times ranging from fractions of seconds to millions of years. So let's take a look at an example. The half-life of a radioactive element is 65 minutes. After 260 minutes, how much of a 40-gram sample of pure Y will be left as Y? Oh, my favorite element, the theoretical Y. So for each of these values, let's identify what it is. We're waiting 65 minutes, or sorry, the half-life. Again, you can use this little symbol here, T half-life, is that the time that we waited is 260 minutes. So maybe right off the bat, we can get the number of half-lives, which is the total time divided by the time for a half-life. So in this case, it would be 260 minutes divided by 65 minutes, which is Nice round number. That is 4 half-lives. So in our equation, n is equal to n0 1/2 raised to the power n. 40 grams is what we started with, 1/2 raised to the power of 4. And so in the end, we should have 2.5 grams remaining as element Y. What happened to the other 37.5 grams? Just to make sure everyone's clear on this, because I think in math you don't really concern yourself with that. 2.5 is element Y. And then the other 37.5 grams, other products of this decay. So again, we're not going to forget that there's still other material involved here. This is the part that we solve for. How much is remaining as element Y? On the flip side, there's still some material there that is the daughter nuclei. But again, the daughter might be radioactive and decay into another nuclei. But for this calculation, it's either element Y or it's something else.